Suppose we have this function of two variables that is a algebraic function. This is an example of a rational function. Rational function is continuous everywhere except where it is undefined, as opposed to polynomials, for instance, that are continuous absolutely everywhere. Where does it fail to be continuous? X squared equals y squared. So then if we take the square root of both sides of this, we get that the absolute value of x cannot equal the absolute value of y. So if we take a look at the xy plane, here's where y is equal to x, which would also cover a case of minus x equals minus y, but also along this line. So here's y equals x, y equals minus x. So those are the places in the xy plane where this function is not defined and therefore is not continuous. Now in this case, this function, we have a linear function up top, we have a quadratic function down below. So as x and y get larger and larger, this function tends to get quite small. It actually goes to 0 as x and y together go to infinity. But you could have rational functions like, for instance, like this, linear function up top. This is not continuous everywhere either. It's not continuous when not defined, where x is equal to minus y. But as x and y become infinite, going to plus infinity or minus infinity, then this function actually is bounded as the sizes of x and y go to infinity. So for instance, if x and y are both going to positive infinity, infinity minus infinity is actually an indeterminate form, but this ends up getting larger and larger. So what can happen is the function, in some direction, some paths might go to 0, on some other paths it might go towards 1. So when the degrees are equal like this, a function tends to remain bounded. Here is a function that tends to be quite small, it's approximately 0 most places. Whereas if a degree of a top is higher, then it behaves more like a polynomial function in most cases. Rational functions are quite useful in my world of computational mathematics because a lot of times I like to approximate complicated functions by polynomials because polynomials are the easiest ones to work with. But sometimes they don't do a job very accurately. Rational functions, because they're quotients of polynomials, are a good fallback. Limits. X cubed minus y cubed over x squared plus y squared. We want to limit as xy goes to 0, 0. So we want to figure out what that is, if it exists, and prove that the limit is what we think it is. So we could try, like I mentioned last time, looking along certain paths. So for instance, x equals 0, y goes to 0, y equals 0, x goes to 0. Y equals x, or more broadly, y equals mx, where m is any. That allows you to check, if you leave m undetermined, that allows you to check infinitely many directions much more efficiently than just trial and error like this. Now, these approaches have one thing in common that's important to keep in mind. They're good for two purposes: finding what might be the limit, like getting a candidate value, or this might be useful for proving that the limit does not exist. Trying these strategies could show that you get different values, or maybe that the function might go to infinity as xy approaches 0, 0. So none of these proving conclusively what the limit is, but it is a good way to bring a problem to a conclusion, and that's all we really care about, isn't it? If we try any of these approaches on this function, what appears to be the limit? Well, if you let x and y simultaneously plug both in as 0, then you get 0 over 0, which is an indeterminate form. But if you plug in x equal to 0, you have minus y cubed over y squared, but that simplifies to minus y. Then you let y go to 0. F of 0 y is minus y cubed over y squared minus y, which goes to 0 as y goes to 0. So if there's a limit at all, it's got to be 0. So it goes to 0 at least along this one path. And if we check any of these others, we would also find that the function appears to be going to 0. So can we prove beyond a shadow of a doubt that the limit is 0? So 0 is our candidate. So to prove it, we use the dreaded delta epsilon definition of a limit. So we assume epsilon greater than 0. So can we find a delta so that if this distance between x, y, and 0, 0 is less than delta, does that mean that this distance is less than epsilon? So that's what we need to find out for whatever epsilon we have chosen, which we can choose any positive one at all. So this right here, that's the square root of x squared plus y squared from the definition of the length of a vector, or magnitude of a point. So what we want to do is find an upper bound for this in terms of the square root of x squared plus y squared. Because if we can do that, then that'll tell us how to define delta in terms of epsilon so that this statement actually works. So let's take a look at x cubed minus y cubed over x squared plus y squared. Now, this is yet another one of those good to know things, that this factors to x minus y, x squared plus xy plus y squared. And then we have an x squared plus y squared here. We have it here also. So now we have x squared plus y squared over x squared plus y squared. So let me break this down a bit into two fractions. So this is just 1. And then I'm going to break this up into a product so we can see how to bound it. So we can write x over the square root of x squared plus y squared, and then times y over the square root of x squared plus y squared. So each of these, what's the largest that those can possibly be? Yeah, 1. Because if y is equal to 0, then this is 1 or minus 1, depending on the size of x. So the most it can be in magnitude is 1. Same for this. So, let me be a little more rigorous here. So this is bounded less than or equal to 1 plus this times this. So since each of these can be no bigger than 1, what we get is bounded by 2 absolute value of x minus y. So we come up with a fairly simple expression that is an upper bound for the size of this, but it's not quite what we want. We want to find an upper bound for this in terms of square root of x squared plus y squared, and we're almost there because we can have an upper bound for this in terms of 2 absolute value of x plus absolute value of minus y. What we used here is called the triangle inequality. So the absolute value of a plus b bounded by absolute value of a plus absolute value of b. So we just use that right here. But now each of these we can bound by square root of x squared plus y squared again. So we get 2 x squared plus y squared plus square root of x squared plus y squared. So altogether bounded by 4 x squared plus y squared. So now we've shown that the gap between this function and 0 is less than or equal to 4 times the distance between the point xy and 0, 0. So what we can do to wrap this up, the difference in y values is less than 4 times the distance between x values. We can choose delta to be epsilon over 4. So whatever we have here, we take the inverse relationship, so we're going to divide by 4 in this case. So if the distance between xy and 0, 0, which is just the square root of x squared plus y squared, is less than delta, then the distance between our function and the limit we think it has, 0, which we already know is less than 4 squared of x squared plus y squared, is less than or equal to 4 delta, equal 4 epsilon over 4, which is equal to epsilon. So this is bounded by delta, then this is bounded by epsilon. Therefore, the limit actually is 0. This is a strictly less than here. This is another example of how you use the delta epsilon definition of a limit. That if you can show that the distance between x values and distance between y values are related through relationships like this, then you can find the actual delta that works for the epsilon that you've chosen. Now, example involving continuity. Suppose we have this function is defined piecewise. xy squared over 2x squared plus y squared. Whenever x and y are not equal to 0, 0, and it's equal to 0 if x and y are equal to 0, 0. And the question is, where is f continuous? Now, it's definitely continuous everywhere except 0, 0, because f is a rational function that is defined everywhere except at 0, 0. So all points except 0, 0 are covered just by the type of function that it is. So we need to check what's happening to this as xy goes to 0, 0. So we need to check if the limit as xy goes to 0, 0 of xy squared over 2x squared plus y squared is actually equal to f of 0, 0, which was defined to be 0. So we've said that the value is 0. So if the limit as xy goes to 0, 0 equals a function value, those two match up, then the function is continuous at that point as well. Therefore, we can say that it's continuous everywhere. So what you do is you go through this process again. You try to get an idea what is the limit of this function. If you set x equal to y, for instance, you get x cubed over 2x squared plus x squared cubed over 3x squared equals x over 3, which goes to 0 as x and y head to the origin. So this, once again, is our candidate for the limit. So that's promising, at least. It appears to be going to 0, but then you have to use the delta epsilon definition once again to prove it, and that means, following a similar approach to what we did last time, we need to find an upper bound for this in terms of x squared plus y squared. So now this is what we're going to be working with. So let's break this up a little bit, pull out absolute value of x, and then we have everything else here. Now let's take a look at that. What is the largest that this can possibly be? 1. So when x is 0, this thing is equal to 1. Otherwise, x is 2x squared is going to make a positive contribution. It'll make the denominator larger. So this is less than or equal to 1. So this whole thing is less than or equal to x, which in turn is less than or equal to x squared plus y squared. If the difference in y values is